All right, guys. In our last class, we learned about how the second derivative allows us to deal with concavity. And so let's see how we can apply that to a really cool application. So what are the critical values of this function? Go ahead and find them on your own. Hopefully you recognize that critical values mean where f prime is 0 or undefined. And this will never be undefined because it'll never be dividing by 0 or taking the square root of a negative. And so we just look for where it's 0. And so we're going to find the derivative. This is power rule. We multiply by the power. 3 times 1/3 is just 1. Lower the power by 1. 2 times a half is 1. Lower the power by 1. And the derivative of 20x is 20. We want this to be equal to 0. Make sure in your work you're putting equals 0 there. So we're factoring -5 and +4 multiply together to make -20 and add to be -1. And so x equals 5 and x equals -4 are the critical values. Now, before we learned how to use a sign chart to see whether the slope was changing from positive to negative or negative to positive. But there's another cool trick you can use using the second derivative. So think for just a second to yourself about how you might be able to use the second derivative. If you know the slope is 0, right, because it's a critical value, how might the second derivative tell you about critical values? Remember, the second derivative tells you about concavity. So how could that be used to tell you whether something's a local minimum or a local maximum? Well, if the slope is 0 and a function is concave up, that function will be a local minimum. If a slope is 0 and that function is concave down, that function will be a local maximum. So we can use the second derivative to see. So rather than make a sign chart, find the second derivative. F prime prime of x is equal to, the derivative of this is what? So it's 2x minus 1, and we aren't making a sign chart or setting this equal to 0. We're literally taking these values. These are the places where we know the slope is 0 already, and so we're going to plug these numbers into the second derivative to see what the concavity is there. So f prime prime of 5, the second derivative at 5 is 2 times 5 minus 1, which is 9. And what's important is that's a positive number. So that tells you that f is what? F is concave up here. And if the function is concave up and has a slope of 0, then 5 must be a local min. How about 4? Go ahead and classify that on your, or -4. Go ahead and classify -4. Well, hopefully what you did was you did f prime prime of -4. So you plugged in -4 and got -9. Now that's a negative number. And since the second derivative is negative, that tells you that f is concave down. And with the additional piece of knowledge that the slope was 0 there, if the slope was 0 and it's concave down, then we know that this is a local max. So here's the second derivative test. Now be careful because both of these things have to be true. If the derivative is 0 and the second derivative is above 0, then, so it's saying if the slope is 0 and the second derivative is above 0, so the second derivative is positive, the slope is 0, well, second derivative being positive means that the function's concave up. And so this is a local min. If the derivative is 0, so the slope is 0, but the second derivative is concave down, is negative, so the function's concave down, then we'll have a local max. Actually, I remember when I was in calculus in high school, this was one of the things I really needed to go back and make sure I got straight for the AP exam. I was like, well, it seems weird that when the second derivative is positive, it would be a min, and when it's negative, there would be a max. Really, in your head, instead of thinking oh, second derivative is positive, think, well, what does the second derivative being positive tell you? That the function is concave up. And so yes, there'll be a min. Now, just because the second derivative is positive does not mean there's a min. Right? A function could be concave up, and maybe you're right here. Here, the function is concave up. Is this a min? No. You need two things. The second derivative needs to be positive, and the first derivative needs to be 0. That's a min. So be careful. Sometimes kids will be like, oh, the second derivative is positive, so there's a min. No, the second derivative needs to be positive and the derivative needs to be 0. So if you're like at this point where the second derivative is positive and the first derivative is 0, then we'll have a local min. All right, so guys, so why didn't we just do this the first time? Why did we make sign charts? This seems a lot faster. Well, it turns out that this won't always work, and you'll see that in one of these examples. Go ahead and use the second derivative to classify the critical values. So first, find the critical values, and then classify them as local mins or maxes, and justify. We'll do the justification of the first one together. But go ahead and find the local, what are the critical values? Hopefully you found the critical values by setting this equal to 0. So 3x squared plus 12x. Where is that equal to 0? These are the critical values. And so we need to factor 3x times x. 3x times 4 is 12x. And so x equals 0 and x equals -4. Those are our critical values. Now we are going to use the second derivative to classify them. So f prime prime is what? So f prime prime is the derivative of the derivative, which is 6x plus 12. And when we plug in 0, f prime prime of 0 is equal to 12, which is greater than 0. It's a positive number. F prime prime of -4 is going to be 6 times -4 is -24. -24 plus 12 is -12, which is a negative. So this tells us that, so let me show you how we do our justification here. Well, let's say what these are first. The function is concave up, then this will be a min. So at x equals 0, there's a min. And if the function is concave down and the slope is 0, this will be a max. Let's write a sentence here justifying this. So f has a local min at x equals 0 because, so here's our justification. How did we know there's a min? Well, there's two parts. First, f prime of 0 equals 0, and f prime of 0 was greater than 0. So, or you could say is positive, right? So, oh, sorry, what's wrong with this? This should say f prime prime is positive. So the derivative is 0, and the second derivative is positive. So if the derivative is 0, but the function's concave up, there's going to be a minimum. Try the justification of the second part on your own. F has a local max at x equals -4 because what? Well, it's because f prime of -4 equals 0, and f prime prime of -4 is less than 0. So the function has a slope of 0 and is concave down. That's why there's a maximum. And this should make sense, right? Okay, it's not moving. There's a slope of 0 and it's bending downwards. That must be a maximum. Now let's see what happens on this one. What's the critical value here? Well, the derivative is 4x cubed, and this is equal to 0 when x equals 0. That's the only critical value. So let's try using the second derivative here. The second derivative is 12x squared, and we plug in 0, g prime prime of 0. So we're going to plug in the critical value is 0. And this isn't positive, and it's not negative, and so the second derivative test fails. The second derivative test only tells you something if it's concave up or concave down. But if you don't know the concavity, then it doesn't tell you anything. Does that mean there's no max or min? No, not necessarily. We're going to go ahead and do a sign chart here. G prime. So the only critical value is 0. And when we pick a number less than 0, the derivative, the slopes, are going to be negative. When we pick a number bigger than 0, the slopes are going to be positive. And if the slopes change from negative to positive, there was a local min. So be careful. The second derivative, if the second derivative is 0 or is undefined, then the second derivative won't tell us anything, and we might still have to make a sign chart. Okay, so the second derivative test is great. If you take the derivative and find the critical values, it's a great idea. If it's easy, if it's easy to take the second derivative, take the second derivative. If it's hard, you might want to just make a sign chart. And the second derivative will usually be able to tell you, it'll tell you whether it's a minimum or maximum, but sometimes it won't, and then you'll have to make a sign chart. There's another issue which is sometimes you don't have the ability to make a sign chart. So we'll see here that sometimes, oh man, I'll go over this with you guys. Sometimes they just give you individual values, and this is not a sign chart. This might kind of remind you of something where it's saying like, okay, x, f prime, and they've got at 1, it's 0, and to the left of 1, it's negative, and then at 5, it's 0. Between these, it's positive. First of all, we don't know what it is on the other side of 5. So we don't know what that is. So we wouldn't be able to tell if this is a minimum or a maximum at x equals 5. But there's another problem here, which is that it looks like it's negative and positive, but this might not be right. And the reason it might not be right is it doesn't tell us that these are all of the critical values. And so there might be like maybe it goes like this. Maybe it's like at 1, it's 0, right? And then at 3, it's also 0. And between here and here, it's really negative. And then between here and here, it becomes positive. And you know, like it's switching signs somewhere along the way. And it can be hard to tell sometimes whether it's switching signs or not. So the second derivative, though, will be able to give us more information. So let's see. Is each statement true or false? And we want to be able to justify. At x equals 5, f of x has a local min. So at x equals 5, is that a local min? Well, I see that the slope is 0, and I see that the second derivative is positive. So the slope is 0, and the second derivative being positive means the function is concave up, and so that must mean there is a local min. This is true. What is the justification? F has a local min at x equals 5 because f prime of 5 is 0 and f prime prime of 5 is greater than 0. So we need both of these things in our justification. The slope was 0 and it was concave up. Therefore, if either one of these things was missing, if the second derivative wasn't positive, then maybe it would be a slope of 0 and it would be a maximum. If the first derivative wasn't 0, well, maybe it's not like a maximum or a minimum because it's just someplace on a concave up shape. So we need the slope is 0 and the second derivative is positive. Okay, at x equals 4, f of x has a local max. Is that true or false? Well, here I see that the second derivative is positive, so it's concave down, but the slope is not 0. The slope is 2, so we must be on like this part of a concave down shape, and there is no local max or min. If the derivative isn't 0 or undefined, you're not going to have a max or min. So this is false. At x equals 1, f of x has a local min. So is that true or false? Well, at x equals 1, we see that the slope is 0. And the function is concave down. It's bending downwards. And if it's bending downwards, this must be a local max. So false. And the reason is because f prime prime is less than 0. And if the function is bending downward, there's no way for there to be a local minimum. At x equals 4, f of x is decreasing. At x equals 4, f of x is decreasing. I see the second derivative is negative, the first derivative is positive. Which one of these tells me about whether it's decreasing or increasing? That's the first derivative. The second derivative tells you about how it's bending. The first derivative tells you about the slope, and the slope is positive 2, so it's bending downwards. We're on like this part of a, oh, you guys can't see this. We're on like this part of, you couldn't see this earlier either. This point at 4 is when the function is bending downwards, but has a positive slope. So there isn't a minimum or maximum there, and it's increasing. This is also false. How about at x equals -2, the function is concave down? Well, this is just f prime prime of -2 needs to be less than 0, and it is not. This is also false because the second derivative is positive, and that's concavity being concave up. Okay. The first derivative being negative means that the function, so the function's concave up because it's a positive second derivative, but the derivative is negative, so it must be like someplace like this. Okay. All right, let's see how we do with this knowledge. Oh, I just want to really quickly, hold on. Give me just 1 second here. Okay, I just want to really quickly show here that this sign, if you treated this like a sign chart, you might think there was a local minimum at x equals 1, because the slope looks like it's negative to the left of 0, and it looks like it's positive to the right of 0. But at 0, the second derivative is negative. The slope is 0 and it's concave down. So how could it be possible that the slope is positive to the right? Well, somewhere between 1 and 4, there must be another slope of 0, giving it time to go back up to having a slope of 4. Somewhere between 1 and -2, it must have another 0 where it goes back up and gives you a chance to have another slope that's negative. When we make a sign chart, there's a key feature, which is that we are not missing any of the critical values. And that's why we talked about how important it is to put them in order from left to right and not be missing any, because if you're missing some, it can give you bad information. This clearly was missing some of the critical values, which is why the second derivative was needed to tell us the real story. Okay, guys, go ahead, and it says in this problem, we've got this table with the function and its derivative. It also tells us that the second derivative is always positive. So it's always going to be positive. The function's always concave up. So is f of 0 a local maximum, local minimum, or can it be determined that it's not? Your answer. What do you guys think? Well, we know that the slope is 0, so that's good. You can't tell based on a sign chart because we don't know if there are other critical values, but we know that the second derivative is greater than 0, and so the function must be concave up, and so there's a local minimum. So local min, because what? Because f prime of 0 is 0, and f prime prime of 0 is positive. So, oops, yeah, it's greater than 0, so it's positive. So that's what's going on there. Write the equation of the tangent line at the point where x equals 1. Go ahead and try that. So what do we need for a tangent line? We need y equals m times x minus x1 plus y1. We need a slope, and we'll use f prime for that. And we need a point. So when x is 1, that's our point. When x is 1, the y value, that's f of x, is -4. So there's our point. And we also need the slope, f prime of 1. And we have that as well. F prime of 1 is 5. And so hopefully you were able to write that your tangent line was y equals 5 times x minus 1 minus 4. So this is the tangent line at x equals 1. Use that to approximate f of 1.2. We don't have a value for f of 1.2, but we can use this linear approximation to estimate the value. So f of 1.2 is approximately equal to 5 times, we're just going to put in 1.2 in the tangent line because, you know, at x equals 1, we don't know exactly what's going on, but we do know what the tangent line looks like, and the tangent line will be very close to the real value. So we're just going to put in 1.2 minus 1 minus 4. This is a fine way to keep your answer for the AP exam. You don't have to simplify, but if you wanted to, you could do 1.2 minus 2 is 0.2, 5 times 0.2 is 1, 1 minus 4 is -3. Now, this goes back to our last lesson, is this approximation greater than or less than the actual value of f of 1.2, and why? Well, at x, we were told that the second derivative was positive, and that means the function is bending upwards. So our tangent line, when we estimated the value, we were plugging in a value on the tangent line, and that is guaranteed to be less than the real value. The real value is bending up away from the tangent line, and so our tangent line is an underestimate. So this is less than, and the reason is because of how the function is bending, because f prime prime is above 0. If the function is bending upwards, then the tangent line ends up below the graph. Okay? Let's see how we do on this. We have a differential equation, which we'll learn about more later this year. It just means it gives you an equation with the derivative. The derivative is equal to this, and it also gives you the second derivative. It also gives you a point 1, 2. At the point 0, 1, does f have a local maximum, a local minimum, or neither? Justify your answer. Go ahead and try it. Is it a local minimum or a local maximum, or neither? Well, the first thing we're going to need to see is the slope 0. It's not going to be a local minimum or a maximum if it's not. So let's look at the slope. We're going to plug in 0 for x and 1 for y. So dy dx at 0, 1 is equal to, this is how we write at a point, is equal to 0 times 1 cubed, which is 0. Okay, so the slope is 0. That's good news for it being a local minimum or a local maximum, but we can't really make a sign chart out of this. So instead, we're going to use the second derivative. The second derivative, d squared y dx squared at 0, 1. We're just going to plug in 0, 1 into this. We get 1 times 1 plus 3 times 0 times 1. This is all 0, so we get 1 times 1 is 1. And this number is positive. So that means the slope is 0, and the function is bending upwards. So there's a local min because f prime at, I guess we'll say at the point 0, 1 is equal to 0, and f prime prime at the point 0, 1 is greater than 0. So if the function has a slope of 0, if the function has a slope of 0 and is bending upwards, there's guaranteed to be a local minimum. So we can see how the second derivative and the first derivative work together to give us some information. What's an equation for the tangent line at x equals 1? So what do we need to write an equation for the tangent line? You need a slope and a point. Y equals m times x minus x1 plus y1. So we need the point when x is 1. So when x is 1, what's the y value? Well, it told us over here that we had a point 1, 2. We also need f prime of 1. Ooh, do we have f prime of 1? When x is 1, y is 2, and so we can plug 1, 2 into this. So the slope dy dx at 1, 2 is equal to 1 times 2 cubed. And 2 times 2 times 2 is 8. 1 times 8 is 8. And so here's our slope, and here's our point. So we get y equals 8 times x minus 1 plus 2. In terms of justification on the AP exam, you need to have shown this. You don't have to rewrite this because they already gave it to you, but they didn't tell you the slope at 1 was 8. And if you find that, it needs to be well labeled. I've seen some kids on the AP exam lose this point because they just wrote, like, if you just wrote 1 times 2 cubed equals 8, this is not good enough. You have not like, what is this? Okay, well, this is a true statement. It's like saying 2 plus 2 equals 4. Great. I mean, it's true, but it doesn't show that you knew anything. You need to label that this is the derivative at 1, 2. So somewhere you needed to say that, hey, I found the derivative, and the derivative was 8. That's how I knew the slope was 8. So that kind of thing needs to be, this came from a free response problem on the AP exam. So if you didn't write this, you would have lost a point for getting the slope. You have to show where it came from, that it came from the derivative. Okay, use the tangent line to approximate f of 1.1. Just plug it into the tangent line. This is easy points to get on the AP exam. And again, you don't have to simplify this. This gets you full credit. If you want to, you can do 1.1 minus 1 is 0.1. 8 times 0.1 is 0.8. And so we get 2.8. I guess we should say f of 1.1 is approximately equal to. But they're not really like, it'll take off points for like how you, whether you said y or f of 1.1. Either way is okay. So given that y is above 0 when x is between 1 and 1.1, is this approximation greater or less than the actual value? And guys, anytime they're asking if an approximation is greater than or less than, there's only one trick we use in this class, and it's that, like, you need to see how the function is curving. If the function is concave up, then the approximation will be an underestimate. If the function is concave down, the approximation is an overestimate. And so you're always going to be using the second derivative for this. So let's see. The second derivative is here. How can we tell if it's positive or negative? Well, they told us the y value is positive. And so what we'll get is a positive number, because y cubed is positive. So a positive times a positive times a positive will be a positive, times 1 plus. Now, x squared will always be positive and y squared will always be positive, because when you square a number, it always comes out positive. So you get 1 plus a positive number is a positive number. So like a positive times a positive will be a positive. And so we can tell that the second derivative is positive. based on the fact that the y values were positive. So we get a positive number, and these were squared, right? So squared numbers are always positive. So if the function is concave up, is the approximation greater than or less than f of 1.1? Well, it's greater. The approximation is less than, because the function was bending up and the tangent line will be too low. So less than, because what's the explanation? F prime prime is greater than 0. Okay. All right, guys, that is it. And that's it for this unit in terms of stuff. You got a quiz to see where you're at on this stuff. And then we've got tests to see where we're at overall. I hope you guys have a good rest of your day and are feeling pretty good about all these derivative stuff. Guys, if you're having any trouble with any of these things, I really urge you to go back and rewatch some of the parts you're not sure of, because this is a really important topic that you're going to want to you need to know it really well now, so that when you get back after like Christmas break, you still know it. This is a large part of the AP exam, so make sure you feel good about it. Have a good rest of your day, and I'll see you later.